Hello everyone. Thank you for joining today's session on Design for Compression, Shear and Bending using IS800 2007 code. My name is Surajit Ghosh. I am a structural engineer and I work in Bentley Systems as a structural consultant in Engineering Simulation Group. This is the second part of our ongoing webinar series on Steel Design to IS800 2007 with STAAD.Pro Connect Edition. IS800 2007 is a large code which is followed to design any hot-rolled steel members along with the steel connections. I have delivered the first part of this series. In that session, I have discussed about the prerequisites for member design using IS800 code in STAAD. Standard design sections, primary, combination and load envelope cases required for design, selection of analysis method based on section 4 and annex B. I have also discussed about stability analysis, consideration of global imperfection and section classification, including the recent change in NBC 2016 code. Finally, I have covered slenderness check along with tension member design. In this session, I am going to show you how to design for compression, shear and bending force. I will start with compression member design using section 7 of IS800 code, discuss about the general design rules and also about the web slender section design. Next, I will cover design for shear and bending. As you know, bending capacity varies if the member is subjected to high shear or if the web is susceptible to shear buckling. I will discuss how to consider these conditions in design and I'll show some tricks to minimize the parameter assignment process using some automation. Let's start with compression member design. When a member is subjected to axial compression force, it may fail in two ways. Short columns have a large lateral dimension compared to the length of the member, and tendency to buckle under compressive load is very less. These columns mainly fail by compression yield or crushing. For long columns, length of member is larger compared to its lateral dimension. These columns have a higher slenderness ratio and tends to buckle. So long columns mainly fail by flexural buckling. And with the increase in length compared to radius of gyration, the tendency to buckle increases, which eventually reduces the overall capacity of the member. Now, this buckling strength is further affected by several factors like residual stress, initial bow imperfection, accidental eccentricities of load. Just consider a column which is perfectly straight and load is applied at the center of the cross section, and another column which is already buckled due to imperfection and load application point is shifted apart. For second column, as it is already deformed, lesser compressive load will initiate buckling failure compared to the first one. We have considered the overall geometric imperfection during stability analysis using notional load. So we have applied the notional load to initiate the geometric imperfection. There is another type of imperfection which is this local bow imperfection, and this is considered during compression capacity calculation along with other factors. Imperfection factor is mentioned in table 7 of IS800 code and it depends on the buckling class which is mentioned in table 10. For I section, depending on the overall dimensions of the section, thickness of flange and whether the section is rolled or welded, buckling class is determined for major and minor axis. For other section like channel, angle or hollow sections, buckling class is calculated for both axes from this table and that is used to calculate the imperfection factor. This value is further used to calculate the design compressive stress FCD and design capacity value. One small correction in this context. In the column buckling curve, value in x-axis represents the non-dimensional effective slenderness ratio which is not printed here but corrected in Amendment 1 and also in NBC 2016 code. This is used for manual calculation only and not implemented in STAAD. Equations mentioned under 7.1 are used to calculate the capacity value in STAAD. Euler buckling stress FCC depends on the effective length of the member. Due to applied compressive load, member buckles, and this deformation is not considered in the first order analysis. So code suggests to multiply an approximate length factor which partially considers the deformation of the member depending on the support condition. Under clause 7.2.2, three conditions are mentioned for effective length factor calculation. First one is either use table 11, which defines the effective length factor for ideal condition on basis of end support condition. Effective length is basically the member length between the inflection points. Deformed shape depends on the end support condition, whether the translational and rotational movements are allowed or not, and accordingly the effective length factors are calculated. For frame structure, a more advanced method of calculating the effective length factor is mentioned in Annex D1. For sway or no sway frames, depending on the stiffness of the connecting beams and columns at end nodes, effective length factor is calculated. This is also an approximate method for calculation of effective length, but if you don't consider the deformed shape of members in analysis, then using this equation, effective length can be calculated, which is further used for calculation of Euler buckling stress and compression capacity value. Similarly, for stepped column, equations to calculate the effective length factors are mentioned in Annex D2. At this moment, these equations are not implemented in STAAD, and if you want to use these effective length factors for capacity calculation, then you need to manually calculate the values and provide that using appropriate design parameter. For a large model with hundreds of members, considerable amount of time will be required to calculate and assign the effective length factors. There is another way to automate this whole process using OpenSTAAD macro. I don't want to discuss that in this session. If you want to know more about this, I can arrange a separate session for that. In both clause 7.2.2 and Annex D, could suggest to use this approximate approach if deformed shape of frame is not considered during analysis. If you perform second order analysis, then you are actually considering the second order effects and additional moment generated due to deformed shape in analysis and design. In this case, whether we need to consider the effective length factor or not, code is silent about that. In AISC code for direct analysis method, which is also a second order analysis, code clearly suggests not to consider any effective length factor as secondary effects are already considered during analysis and force is amplified for that. This is more accurate approach as we are considering the deformed shape and its effect on structural behavior rather than decreasing the capacity value by considering some approximate effective length factor. But Indian code does not clarify anything about this and leave it up to the user. You can consult AISC code or Eurocode for better understanding of ELM approach or effective length method for compressing capacity calculation. There are 6 design parameters which controls the compression capacity check. FILD is the yield strength of steel. By default, it is considered as 250 MPa. KY and KZ are the effective length factors, whereas LY and LZ are the effective lengths. I have discussed about these parameters in the last session during discussion on slenderness check. Just one additional information. It is not required to provide both K and L parameters. Either define KY or KZ as an effective length factor or calculate the effective length and specify that using LY or LZ. STP parameter is used to define whether the section is rolled or welded. For buckling class determination using table 10, you need to inform program about the section type, and STP is used for that one. If you use built-up section or welded section in your model, don't forget to assign this STP parameter. Else, program will treat those as a rolled section and the calculation will be incorrect. Consider this column member. Due to compressive load, this column can buckle both in major and minor axis. Now, for major axis buckling, there is a beam member connected at intermediate location and spanning in the perpendicular direction. This beam will provide lateral support to the major axis buckling, and hence the buckling length should be calculated as these distances. If you consider minor axis buckling, there is no intermediate restraint which can resist buckling in minor axis. So the effective length should be calculated from the full member length. How to define this condition in STAAD? Say the length of member 1 and 2 is 5 meter and 3 meter respectively. Calculated Ky and Kz value from Annex D are 0.8 and 0.75. You need to specify Ky and Kz value to both these members and also define Ly value as 8 meter and assign it to both these members. No need to specify Lz as it will be considered as member length by default. For single angle sections loaded through one leg, due to compressive load, member is subjected to flexural torsional buckling as the load is not passing through the centroid. To consider this flexural torsional buckling, slenderness ratio is calculated using clause 7.5.1.2. There are three constants K1, K2 and K3 which are calculated from table 12. To calculate these values, there are three additional parameters which you need to define. Ang is used to specify whether the angle is loaded through one leg or at centroid. Only if the angle is loaded through one leg, then slenderness ratio is calculated using clause 7.5.1.2. Fxty parameter is used to specify the end condition, fixed or hinged, and NBL parameter is used to specify the number of bolts or welds at the end. Note that these parameters are applicable only for single angle section and if the section is loaded through one leg. After design in the output file, buckling class and major and minor axis capacity values are reported along with the critical load number and clause number. Only critical load values are reported for which the compression ratio is maximum. I will discuss the design output in details. For web slender section, nothing is mentioned in section 7 what property value should be used to calculate the compression capacity. Code is completely silent about the web slender section design principles. Instead, it is implemented following the guidelines of Eurocode or EC3 code, as IS800 design rules are almost similar to this code, and Indian Code Committee also considered this code as mentioned in the forward section. In EC3 code, effective area is considered for capacity calculation, but Euler buckling stress is calculated using actual radius of gyration value. So when you design the compression capacity of a web slender section using IS800 code, program considers R value of full section, but area value is calculated based on the effective section only, neglecting the portion which is reduced due to bring back the section to semi-compact limit. Any member which is subjected to a flexural load experience both bending and shear. If you look at the bending and shear stress diagram of an I section, you can notice that flange is subjected to maximum bending stress, whereas web is subjected to shear stress. When we design any section for bending or shear, we consider that bending is resisted predominantly by the flange, whereas shear is resisted by the web. There are three possible conditions of shear failure of a flexural member. Web can fail due to shear yielding. If the shear force in web is greater than the yield strength, then web may fail in yielding due to shear. Now, if the web becomes thin, then due to applied load, web starts to buckle before it reaches the yielding limit. And once the web buckling starts, it never reaches the yielding limit and fails due to buckling before yielding. There is another failure condition which is web crippling, where the web buckles locally due to stress concentration. This failure does not occur at the entire web portion, rather a small portion of the web which is subjected to high stress cripples and fail. For shear design, section 8.4 of IS800 code is used. If you look at the equations, you can notice that first two failure criteria is considered for shear capacity calculation. If yielding of the web governs, then nominal shear resistance is calculated using clause 8.4.1, considering the yield strength of the web. But if the web is subjected to web buckling, then clause 8.4.2 is used to calculate the nominal shear strength. This web buckling limit is checked as mentioned in clause 8.4.2.1 with or without stiffener condition. If the web is very thin and d by tw ratio is greater than 67 epsilon, then web is susceptible to shear buckling. But this can be avoided by adding transverse stiffener. These stiffeners are provided perpendicular to the web, hence reduce the chance of buckling by providing support in the lateral direction. Thin web tends to buckle outwards, and this stiffener resists this outward buckling. You can notice that web buckling limit increases if you strengthen the web by adding stiffener, as kV increases with addition of stiffener. And with inclusion of more closely spaced stiffener, this limit increases, which means chance of web buckling drastically reduces. This is one reason for providing transverse stiffener in the web. Instead, simple post-critical method as per clause 8.4.2.2a is implemented to calculate the nominal shear strength for shear buckling. Tension field method is not implemented yet. Also, stiffener cannot be modeled or designed in STAAD. You can provide stiffener information, and on basis of that, shear capacity is determined. There are three parameters which controls shear design: LST, TST, and TSP parameters. These three parameters are used to define whether any longitudinal or transverse stiffener is provided or not. By default, STAAD assumes no stiffener is provided, but if you want to include stiffener, you can provide these three parameters. I have discussed about these parameters in my last session for minimum web thickness criteria check. You can go through that part for more details. For shear capacity calculation of web slender section, nothing is specified in IS800 code, and in NBC 2016 code, it is mentioned that shear capacity should be calculated considering the web buckling criteria. Though NBC 2016 is not implemented in STAAD, but for web slender section, as the d by tw ratio is greater than 67 epsilon or the limiting value with transverse stiffener, so instead clause 8.4.2.2a is used to calculate the shear capacity value. For bending capacity, design provisions mentioned in IS800 code are not properly clarified. Code suggests design rules for individual and general cases, but for specific cases like web slender section, how to consider the clauses, it is unclear. I will discuss this shortly and also let you know how we interpret the clauses and how it is implemented in STAAD. Any flexural member can fail in bending for multiple reasons like flange yielding, lateral torsional buckling, tension or compression flange local buckling. Among all these failure criteria, Indian Code considers two types of failure in capacity calculation. First one is the lateral torsional buckling and second one is the yielding. Most critical failure for any unrestrained beam in flexure is the lateral torsional buckling failure. Unrestrained or unsupported flexural member means compression flange of the member is not restricted against lateral movement and rotation. For example, consider this simply supported member where an UDL is applied. This beam bends due to the moment and top flange or the compression flange will deflect downwards. Also, the compression flange tries to deflect laterally away from its original position. Now, we assume that the load is applied at the center, which produces equal stress at two extreme fiber of flange. But in reality, it is not true, and due to imperfection in the beam or accidental eccentricity in loading, different stresses are generated. Furthermore, residual stresses contribute to unequal stress across the flange, which results a twisting action about the longitudinal axis. So the beam will not only move laterally but also experience a twist which we termed as lateral torsional buckling. Most of the cases, this results beam failure and we need to calculate the elastic critical buckling moment or MCR value to ensure proper resistance against this. I have created this cantilever I section in physical modeler mode using finite element meshing. Both wave and flange is created using plate elements and I have applied a UDL on the top flange with some eccentricity value. I have analyzed this in analytical modeler and look at the deflection diagram of this member. You can see due to the applied flexural load, this beam is both deflecting laterally and also in the downward direction. And not only that, there is a twisting movement along the longitudinal axis. This is what we called as the lateral torsional buckling, and this can lead to failure if not considered during design. There are multiple factors which govern the lateral torsional buckling. Different support conditions and effective length for lateral torsional buckling are the two major factors which affect the MCR value. Simple example is fixed support which does not allow any rotational or translational movement is less vulnerable than the simple support. In table 15 of IS800 code, depending on the support restraint condition, effective length factors are provided and this needs to be considered for MCR calculation. In this table, end conditions are only considered and if there is any intermediate restraint, then effective length should be calculated using 8.3.1 to 8.3.4. Basically, the distance between the restraints are considered here. Also notice that two types of loading conditions are mentioned in this table. That is because the lateral torsional buckling depends on the location of the applied load. If the load is applied above the shear center of the cross section, then it amplifies the torsional buckling effect, hence termed as destabilizing load. Whereas any load applied at or below the shear center tries to reduce the susceptibility of the section to the effects of lateral torsional buckling. There are other factors also. Different cross-section shapes like open or closed section has different resistance to lateral torsional buckling. Open sections are more vulnerable to lateral torsional buckling rather than closed or hollow sections as these sections have higher torsional resistance. I'll discuss how code handles the effect of shapes on bending capacity calculation shortly. Finally, the load pattern has some major role on this. The buckling resistance of a section subjected to uniform bending moment distribution along its length is less than the same subjected to a different bending moment distribution. In Annex E of IS800 code, a detailed formula is provided to calculate the MCR value for sections which are symmetric about minor axis with major axis bending. In this equation, you can notice all these factors are considered, like yg is the distance between the load application point and shear center. It is considered as negative if load is applied below the shear center or stabilizing load. LLT is the effective length factor. Factor C1, C2 and C3 are calculated from table 42, and these values depend on both end condition and also on the bending moment diagram. It is very hard to calculate these factors manually, as for different load cases, bending pattern may different. This equation is not implemented in STAAD. A simplified equation for symmetric section is mentioned in clause 8.2.2.1, which is implemented in STAAD, and MCR value is calculated based on this, which further used to calculate the bending capacity value. Note that the imperfection factor for bending depends on section type. Hence, proper STP parameter assignment is necessary for bending capacity calculation. If you want to minimize lateral torsional buckling, you can either provide intermediate lateral restraint to resist the lateral and twisting movement, or you can also increase the flange thickness. The twisting is resisted by the torsional stiffness of the section, and torsional stiffness is dominated by the flange thickness. That is why a section with higher flange has a larger bending strength than the same depth of section with thinner flange. Now, code suggests that lateral torsional buckling effect can be neglected if the bending is about minor axis. For hollow sections, where the chance of lateral torsional buckling is very nominal, and also if the non-dimensional slenderness ratio is less than 0.4 for major axis. Small lambda LT value indicates large MCR value, which means chance of lateral torsional buckling is very nominal. In such cases, bending capacity is calculated only for yielding. Also, if the compression flange is adequately restrained against lateral and torsional movement, then we consider that beam as laterally supported, and in all these conditions, clause 8.2.1 is used to calculate the bending capacity value. Under this, you can notice three conditions. 8.2.1.1 defines the bending capacity calculation rules when the wave is susceptible to shear buckling or D by TW ratio is greater than 67 epsilon, as discussed earlier. In such case, we consider the first approach. Bending is resisted by the flange alone and wave resists the shear. In this case, wave is completely switched off and modified property values are calculated considering only the flange, and that is used to calculate the bending capacity value. If the wave is not susceptible to shear buckling, and if applied shear force is less than 60% of shear capacity of the section, then clause 8.2.1.2 is used for bending capacity calculation. This equation basically considers the yielding failure, and for plastic and compact section, though the plastic section modulus is used to calculate the bending capacity, still it is cross-checked against 1.2 or 1.5 times the elastic yielding limit. For this, you need to specify the CAN parameter. I will discuss this shortly. There is another condition when member is subjected to high shear. Bending and shear is not independent, rather they affect each other. In high shear case, clause 9.2 is used, which is basically an interaction check with shear and bending condition. In this clause, you can notice that code suggests no reduction is necessary if the member is subjected to low shear, and only if the shear force is greater than 60% of shear capacity, then the bending capacity must be reduced proportionally of the shear force. Consider this equation MD is calculated considering full section and MFD is calculated for flange only. This beta is a reduction factor, and if shear force increases, this factor also increases. MD minus MFD is the bending capacity contribution of the wave portion. So you are actually reducing the overall bending capacity of the section proportionately to the applied shear force. Means you are switching off the wave contribution on bending capacity if shear value increases, assuming wave is meant to resist the shear first, and then rest of the excess wave capacity can be utilized to resist the bending. Clear? This is what is meant in this clause for high shear case. These equations and design principles are implemented in STAAD. I know it seems a bit complicated. There are another few conditions which I have not discussed in this session, like bending capacity for wave slender section, general rules, and also for high shear and low shear case. IS800 code doesn't clarify about this, though NBC code suggests to consider the wave buckling criteria for wave slender section design. We have been discussing with the code committee for clarification of the design rules for bending capacity calculation of wave slender section. Meanwhile, it is implemented in STAAD with help of other international design codes. If you need any further information about this, you can comment in the survey window. There are 6 parameters which controls the bending capacity calculation. The first one is can parameter. This is used to define beam type, whether the beam is cantilever or simply supported. It is used in clause 8.2.1.2, and if you assign can parameter as 0, then these additional checks will not be performed. Lat parameter is used to define whether the member is laterally supported or unsupported, and accordingly program performs the lateral torsional buckling check. By default, program considers all member laterally unrestrained. If you model a composite deck structure where the concrete slab sits on top of the I section, you can assume full restraint against lateral torsional buckling. In such condition, lat1 parameter needs to be assigned. If you provide intermediate restraint, then you can define the member as laterally unsupported and provide the distance between the lateral restraint using effective length parameter Lx or Kx. These are the effective length factors used for MCR calculation, as mentioned in table 15. In other code like AISC code, two different parameters UNT and UNB are available to define separate restraint length for top and bottom flange. For Indian code, effective length for top and bottom flange is considered to be same. And finally, you need to provide both FYLD and STP parameter as discussed earlier. STP parameter assignment for built-up section is very important as this affects several design results. In older version of STAAD, like in the VATI version or in earlier version of Connect Edition, there were several changes to these design principles. Like if you consider wave buckling criteria, for low shear case also, section property was reduced. There are few changes related to lateral torsional buckling in recent version. So there might be some value mismatch with older version. Older results were not incorrect, but those were in conservative side. This is all about bending. Due to limited time, I tried to cover only the basic and implementation of different clause in STAAD and skipped some advanced discussion. I can arrange a detailed session later if you want. I have discussed about so many parameters. Few more are required for interaction check. Now in STAAD, no table is generated for design parameters like beam or node table, and if you want to check whether any design parameter is assigned to a member or not, you need to either manually search from the input editor or from the parameter table, which is time consuming. I have created an OpenSTAAD macro which can generate the design parameter table easily, either in Excel or in GUI. For example, this is the Excel macro. If there are multiple design parameter blocks, I need to provide only the parameter number, and all design parameter value for all members are extracted in this table, as you can see here. This includes default value as well as the user defined value. From this list, you can easily check what is the value of any parameter for any member present in this model. Similarly, you can add this macro in the user tools of your STAAD window and run it anytime you require by specifying the parameter block number, and a table is generated with all the design parameter information. Only problem in this table is the decimal places, which is hard coded. I can't change the decimal places. But I think you can easily check the values from this table rather than searching from the editor file. There are lots of things you can do using OpenSTAAD tools. If you are interested, you can check my videos from the YouTube channel or from my LinkedIn page. Now I want to talk about the design principles followed in STAAD. When you perform member design in STAAD, program divides each member in 12 sections. That means there are 11 intermediate design points along with the start and end node of the member. All total 13 design sections. These 13 sections are designed individually for all load cases. Consider this 12-meter beam with a uniform eye profile. I want to design this member using IS800 code, and there are 5 load combination cases. Program first finds out the location of those 11 intermediate sections, and all member force values for each load case is computed from the analysis results. Let's consider section 5 and load case 1. For this section, on basis of the section dimension, overall design input and force values, section class is determined first from table 2, and all capacity and design ratio values are computed. So for this section, for load case 1, we have different design ratio values for axial, shear, bending and interaction check. This is repeated for rest of the load cases, and at this section, we now have 5 sets of design ratio values for 5 load cases. Repeat this whole process for all 13 sections. This means after design of all sections for all load cases, we have 13 into 5 number of ratio values for each design check, whether it is compression, shear or bending. Among these 65 ratio values, the maximum one is reported in the output in corresponding category. For example, if you check bending or shear output, the critical ratio is reported from the set of results, the maximum one, and load case number and location of the maximum ratio is reported along with the force and capacity value at the section. And considering all sections, all load cases, all design checks, the maximum ratio value is reported as the critical design ratio along with the design clauses force values. Section class force values corresponding to the section is reported here. So this section class which is reported in the output file is the section class of the critical section only. And it may happen that for other section, different section class is computed which is not reported as that section is not critical. If you want to validate STAAD results with your manual calculation, cross-check the section classification also. And if this does not match with STAAD, check the section for which it is reported and the section which you have considered. For tapered section, section class varies considerably along the member length and it is correctly considered during design. I'll cover this in next session. STAAD output file has two parts. First page reports the critical most design outputs, including the design property value, forces and section class. All these force property are at critical section only and also for critical load case. Second page reports highest results for individual check for tension, compression, shear, bending, and interaction check. For shear and bending, capacity and force values in major and minor axis are reported with critical location and clause number. And finally, a table is printed where the maximum ratio for each check along with load case and location is reported. There is one parameter, beam, using which you can minimize the design sections. By default, program designs at 13 sections, but if you define beam parameter along with section command, then program designs the member at end and those locations specified in the section command. In post-processing mode, you can check the unity ratio from utilization table and also in the GUI. The unity ratio values are reported along different color of each member, which depends on the ratio value. You can change the color from the design result diagram, use basic diagram or detail diagram, and provide ratio limit for each color. It will help to understand the range of utilization ratio from GUI. In utilization table, three ratio values are printed. Actual ratio is the calculated ratio value. Allowable ratio is normally considered as 1, which means the ratio of actual force and allowable capacity is 1. Now, if you don't want to consider full capacity and want to apply a factor of safety by considering a percentage of actual capacity, then you can define that using ratio parameter. For example, if you want to consider the actual force to be less than 90% of capacity, then you need to specify 0.9 as ratio and that will be considered as allowable ratio. And ratio of actual and allowable value is printed in normalized ratio table. List of failed members are reported in the failure table where you can check the final ratio value and critical clause. You can also check how many members failed using some custom user tools. I have created and imported this tool. This helps me a lot to select proper section in manual iteration process. How the number of failed member reduced in each iteration after changing the section and redesign. That's all from my side today. I'll cover serviceability design in the next part along with the interaction, web tapered and built up section design, and discussion on section 12 for earthquake load. Hope to see you all in the next session.